All right. Let's share the window. Oh, we show the entire screen. All right, cool. What's up? Oh, we got 6 people in here. What's up, guys? What's up, guys? You guys hear me okay? Yes, Michael says yes. Welcome back, Michael, dude. Congratulations on making it to all 3 sessions here. Very good job. I know that second one was actually kind of early for probably the West Coast or Central Coast students, because that was at 5 o'clock for 2 o'clock for West Coast students. So that's a little early for you guys to be in school. So I moved this one to 5 p.m. to give you guys a chance. But okay, cool. All right, we'll give like 4 or 5 minutes for everyone to roll in, and then we'll start work on things. What's up, Amina? Good to see you. How have you guys been doing with AP exams this week? You're probably like really glad to almost be done, right? There's only like 1 or 2 more days left, I think, for this week. One last tomorrow. Ooh, nice. I had AP language yesterday. Ooh, wow. AP language. Is that the one where you have to write like all these huge like essays, or is that different? I forget if like there's AP language or like AP writing or like AP literature. Physics tomorrow, right? Yeah, well that's why we're here. We're here to make sure you guys are ready for physics tomorrow. This is my last one, but it doesn't feel like it, Sophia. Oh no. we didn't have school. Oh, there's a fire nearby. Oh no. What? There was a fire? Where's there a fire? Is this California? California's like always burning down. 3 essays in 2 hours? Wow. Yeah. My hand would hurt. I don't know if I'd be able to like write for 3 essays in 2 hours. Nah. You know, I'd be like, no, please. No, I don't want to do that. Oh, it's in Jemez, New Mexico. Okay, interesting. I did when I was in. Oh, I actually want to see where that is real quick. Let me check. I actually want to see where that is. Maps.google, or let's say Jemez Google Maps, New Mexico. Let's see where that is. Curious. Jemez Pueblo, is it over here? Whatever, it's over here. Okay. Oh, up by Albuquerque. Okay. Interesting. Very cool. They canceled the AP physics test for you guys because of the fire? Oh, wow. That's nuts. So, where is it? Oh, yeah, Los Alamos. So I in college, I did an internship at Los Alamos it was for physics. It was for plasma physics. It was an internship. And so, wow, that's pretty close. That's right down here. Yeah, I remember Los Alamos I stayed in for a while. Santa Fe I call like the city of turquoise. But yeah, that's interesting. There's a fire there. Well, hope you guys stay safe and whatnot. I wrote so much I almost bruised my finger. Oh no. I wonder if it like at some point like they're just gonna give you guys keyboards and be like, just type, you know? Like, come on. Like, who actually handwrites anything these days? Like I did. I hand wrote some things for you guys. But nowadays everything's just on an iPad or you just get on a keyboard. There are kids that wear band-aids. Okay, that's cruel. Like, what? They shouldn't be like putting you guys through like that much torture to like do an AP exam. Like, it's already hard enough to like study for this thing, and now like to take it is like a physical like exercise. All right. Well, cool. We got well here we'll start some things off just to you know make use of the time and whatnot. So welcome everyone. My name's Dr. Gold. I'm here to help you guys out with AP Physics 1. Exam is tomorrow. In the last 2 sessions, we went over the free response questions for 2021, the most recent ones. And I hope that was useful in like, you know, figuring out like little strategies to solve the FRQs and how to, you know, best approach things and solve them. With the exam tomorrow, I want to do kind of a little bit of like some like last little quick tips that can help you on the exam. As well as what I did is I went through all the previous year's exams and I looked at which free response questions had the lowest scores. So like basically which ones were the toughest. And I figured with the amount of time we have, we can go through some of those. Unless if you guys also have like a specific topic where you're like, I really need help in blank, or I'm really not good at, you know, you know, I don't know, say like gravity or something, I can also find a question that's over that, and we can do that. If there's like, if everyone's like, I don't understand springs or whatnot, it's like, cool, we can do a spring problem to help you guys out. So in the chat, if you have anything like specifically, you know, maybe say what, you know, is really giving you trouble, and I'll try to see if we can find a question that's related to it. But what I wanted to show you guys first is this cool sheet that our friend here, Jonathan from Flipping Physics made, which is he's made so many sheets to help you guys out with this exam. Okay, rotational motion. Okay, cool. Yes, well, I always hear people like need help with rotational motion. But anyways, so Jonathan has done, he's made a ton of really cool PDFs that help out with you know, getting ready for this AP Physics 1 exam and whatnot. And one of the sheets he's done here is this last little summary thing of equations to memorize. So these are equations that aren't covered in the equation sheet that you get on the exam. So if we remember right over here, right, there's this lovely huge equation sheet that you get that you guys can use to pretty much figure out stuff that you don't know. But some of the equations that you do need to know in the exam aren't really on this sheet. And so what Jonathan has done very nice for us and for you guys is he's made a little sheet here that you guys can go through. So I'll go through it real quickly, some things here. So he talks about here, speed is distance over time, and v is velocity, which is change in position over time, and acceleration is change in velocity over time. That's interesting. Do they not put that? Wow, they don't put that on the equation sheet. Wow, that's a very important thing to know. Okay, cool. All right. So yes, you guys should always, you should, in your study of kinematics, very much should know, right? Velocity is change in position, acceleration is change in velocity. Can I put the link in the chat? Yes. So let me think. One sec. I gotta make a little Dropbox link for you guys real quick. Where did I put it? Copy. Where is Dropbox? Share. Copy Dropbox link. Here we go. Yes, can I have that? There you go. There's a Dropbox link for it. You can also access this if you go to what is it? ap1kudu.actual.education. This is another cool website. ap1kudu.actual.education. All good if you missed the first one. This is a free course that we've made with our friends here at Kudu. That is a whole like AP1 review course that you can go through, and it has a bunch of different questions and cool videos and practice multiple choice stuff that you can do. You can sign up for free. It's totally free. Just use the link there. You might have to click it, create an account, and then click it again to sign up. The recordings are down, although for some reason, I got to talk to Sorsh about this. The second session didn't record completely. Like it only recorded the last 3 minutes. So I don't know. The first one is definitely there. There's a recording there at the bottom. I also put it on, one second. Let me see. I put it on a YouTube. Let's see, YouTube. If you guys want to watch it on YouTube, I also put it right here. I'll give you guys that link as well. Yeah, the second one, I don't know why the second one's only 30 seconds long. Honestly, I got to ask Sorsh about that. Maybe I can get that fixed. But this was, hopefully this isn't as choppy. But yeah, okay, there you go. So I have a YouTube. I have it on YouTube if you guys want to watch it there as well. This is also my YouTube channel where I do a bunch of quick videos, and these are all the tutoring sessions I also do for free that you guys can take a look at if you want. But anyways, the Kudu course here is very cool. If you go to any of these sections, let's say for instance, some of you guys were saying I have problems with momentum, right? You could click here on momentum. There's a cool video here done by Jonathan with Flipping Physics that you can watch, where this is a cool little, look at this, 5-6 minutes, very quick. He does an excellent job. He's a great guy, Jonathan. And you can just watch a quick little review video on, you know, linear momentum and impulse, if that's what you need a little bit of help with. And then if you click here, I know this is kind of hard to see sometimes. You got to click here on lecture notes. Here's another PDF that includes everything you need to know about just linear momentum and impulse. And you guys can just, these are all free resources. You can just use this, print it out, look at it, whatnot. And then below, there are a bunch of questions here that relate to the video. And you have to answer these first, actually. And don't worry about, you don't have to answer them correctly. So like, if you really want to, you could just do, you know, blah, blah, Well, let's just put the, you should answer these but if you don't have time and you just want to go to the multiple choice questions that are based on the AP exam, you can do that by here. Let's just wait. Do I have to answer all of them? Let me see. Maybe I do have to answer all of them. This is a good question with like how often, what's the percentage I'm going to get right from just answering like randomly B's and C's, right? Let's just see. Okay. And then what this should do, this should unlock it. So if we go back to linear momentum and impulse, now if we go to questions, there you go. These are now, so once you just answer something for the pre-lecture questions, the reason that's set up the way it is they want you to go through the video first before you go through the practice questions. But you can just, nothing's actually here being graded for a grade. So you can just type in whatever. But then you can get down to here. These are professionally written AP Physics 1 multiple choice questions that we had done by a guy named Dan. I need to remember his last name. I'm so bad with names. Dan Brown, I think is his name. Well, Dan Brown's also the writer for that one book. But Dan is his name. Great guy. And he's one of the best AP Physics 1 teachers in the country. He's got like tons of awards and stuff. But he wrote, and his friends wrote a lot of these multiple choice questions. And some of them he's actually written for the AP 1 exam. So this is another cool resource if you guys want to go through and, check, reinforce your multiple choice knowledge. And you can check the answers. If you get it right and whatnot, it'll say, nope, this is wrong. And you can try it again. You can just keep trying till you get it right. There we go. Second time's a charm. Anyways, yes, that's all of that. And then the last section here, important equations to memorize. If you click here on lecture notes, this also has the PDF, which I linked to you guys in the chat. So you can also go through there. Okay. Any quick questions about this? Any like, what the hell is this? How's this work? Type stuff. Thank you. Okay, cool. Awesome. Great. All right. Okay, so let's get moving back on. Okay, so let's go here. Let me leave this. We don't need to look at kudu stuff anymore. Okay. So again, good to know what velocity and acceleration are in terms of position and time. Okay. This is another important one where it says delta x is equal to 1/2 VF plus VI times delta t. So this question, this equation, it refers to things when you have what's called uniform acceleration. Okay. So in the case, in the case of uniform acceleration also means that the forces aren't changing. And this is also a fancy word for just A is constant. Okay. We can represent that the distance something travels, delta x, is equal to 1/2, and this is going to be the average of the initial velocity and the final velocity. So that's why it's 1/2. We say like v initial plus vf times the time. So this is an important one that they don't really put on your sheet here. You can get this also, I think, through the. There is one other. Where's the other? Let me see. You can basically get that equation from. Oh, do they not give you the timeless equation here either? Oh, no, they do. Right here. Right, yeah. You can get it from here if you really want to as well. This is another one that will get you basically the same result. But yes, that's an important one to know. Okay, the F is mg sine theta and mg cosine theta. This is stuff on an incline. You guys should know this from geometry stuff. Whenever you have, for instance, things that are on an incline. Let's draw a straight incline these days. You have an object here, right? We always know that, for instance, mg is going to point down, and then because of that, there's always components to that. Okay, so you have what's called like F parallel. That's the force that pulls this block down, and then you have what's called F perp, which is equal to the force that pulls this thing into the incline, right? which you know is then also going to be equal to what? What is this F perp always equal to? What's this force over here? Just a little quick refresher. Good. Normal force, Fn. Yes, great. Okay. Now, here's the thing. A lot of times what they'll do when they give you these inclines is they'll give you this angle as theta. They'll say this is the angle of the incline. Okay. When that's the case, all right, what ends up happening is that this angle is also equal to this angle. All right. If you want a quick like introduction why that is what it is, okay. First of all, I know that this is a right angle, right? I know this is a right angle, right? And I know that this makes a triangle and this makes a triangle, okay? And even more so that this and this make a right angle, okay? So if you look at this triangle right here, and let's call this like B, right? I know that theta plus 90 degrees plus B has to equal 180 degrees, right? These three angles have to all add up to 180 degrees in a triangle. And this also has to add up to 180 degrees. So, or actually, no, more importantly, this and this, right? Theta plus B, these two have to add up to 90 degrees because this F perp is always perpendicular to the line of the incline. So I know that B plus theta is equal to 90 degrees, right? So what that tells you here, right, is that this theta here must also equal this theta here. Because if we look at this, right, we get theta is equal to theta plus B is equal to 180 minus 90 by minus 90 on both sides. So that's equal to 90 degrees. Let's call this one like theta 1 and theta 2. And these two must add up to 90. And so since they both add up to 90, that means that theta 1 is equal to theta 2. That's a way that you geometrically can prove that this angle is also equal to this angle. The better way I like to do it is I also like to do what's called like limiting cases, which is, let's say, for instance, this incline starts to decrease, right? In that case, right, this angle would also be getting lower, right? And I would expect that the angle between gravity and straight down from the block should also be getting lower. So since this angle gets lower, that means that, and this angle should also get lower, that means that this angle equals this angle. You can kind of see that if, like, let's say like we put it down to here, right? Then the block would have gravity pointing this way, the perpendicular normal force pointing this way, and you can see that this would be a lower angle with this. That's the case of limiting cases. That's a good thing to know. Okay. Yes, so this is usually what's given to you, such that these angles are the same, okay? And that's why F parallel, right, from trigonometry is equal to mg sine theta, okay? Because sine is opposite of hypotenuse. If they end up giving you this angle as being theta, then this is not going to be the same theta, and it's not going to be mg sine theta or mg cosine theta. So you got to be careful about that. I don't think they're going to give you this as the angle, but just watch out. That's just something to look out for. So a lot of times, right, if theta is the incline angle, then this will always hold true. Okay, mechanical energy is conserved when there's no work done by the force of friction or force applied. That's right, right? So mechanical energy, right, is all the 1/2 mv squared stuff. And then we have the work energy theorem here. Can I go over work? Yeah, sure. Yeah, sure. I can do work. Yeah, totally. Right. Okay. Let's here. Let me do a quick one real quick on work. Okay. So work is always equal to F times the distance times, I think this is what, yeah, it's cosine theta, right? Okay. What this really means is the amount of force is mechanical energy, the potential and kinetic energies. I think it's just the kinetic energies. Is it also the potential as well? Mechanical energy. 1 second. Energy. Yes, mechanical energy is both. You're right. Yep. Good. Yep, it is both. And we'll get into why that is, right? Because remember when we were saying conservation of energy holds as long as there's no non-conservative forces. Non-conservative forces are things such as friction and whatnot. And those end up doing work on the system, which will either put energy into the system or take energy out of the system. and that would mess up the balance between kinetic and potential energy, which are all sum up to become mechanical. So work is always force times, I say distance, and then I say in the direction of the force. So the classic one that's always given to you is they'll say, for instance, a block of mass 10 kilograms is on an incline with a 30-degree angle. If the height of the incline is equal to 10 meters, or well, let's give some different numbers. 20 meters. How much work is done by gravity as the block falls? Also changes. Yes. Yeah. Good. As the block falls, as the block slides to the bottom of the incline. Okay. This is a classic question. They love to ask this one because there's a trick to doing this. Let's see if I can make that text bigger. Yeah, cool. All right, here. Let's put this on a new page. Okay. So draw a picture, right? Usually have block here that has a mass, right? And it's located at the, let's say it's at the top of the incline. Let's put it at the top. And this is equal to 10 meters, okay? And then, here, let's make this a little bit smaller. And then this is m equals 10 kilograms, okay? And they want to know what is the work done by gravity as this object goes all the way down to the bottom, okay? So in order to figure that out, isn't it 20? Oh, you're right. The height can, thank you. Yes, you're right. Totally right. 20 meters. Good. And then this is 30 degrees. Okay. All right. So the work done by gravity would be equal to the force of gravity times the distance times the cosine of the angle in between them. Okay. Now this is pretty cool. So yeah. So distance times cosine. Yes. Okay. So in this case, right, gravity is always going to point straight down, right? This is always going to be the force of gravity. Okay. And now what we need to know is the amount of distance that this block travels. Okay. This block technically travels, right, a distance equal to the hypotenuse of this triangle. Okay. Which you could find the distance of that by using trig, right? I would say that, for instance, the sine of 30 degrees is equal to, what is it going to be? Opposite over hypotenuse. So that's going to equal 20 over the hypotenuse, right? So the hypotenuse ends up equaling 20 over sine of 30 degrees, right? Which is 20. Sine of 30, you guys should know, is 1/2. So that just equals to 40, all right? So this is equal to 40. And then, so that's the distance that it travels. So the force of gravity would be equal to the 10, right, times the 9.8, times the distance right here, right, which would be 40, times the cosine of the angle in between the two, right? So this gets a little interesting because it's the cosine of the angle in between the distance and the force of gravity, okay? Now, the distance is pointing in this direction. Gravity is pointing in this direction. They're vectors, right? They have a direction. So this angle is going to end up being, what do you guys think this angle is going to be between the distance and the force of gravity? 60, good. Yes, right. Because this makes a whole triangle, right? This is 30 and this is 60, good. So this is end up being 40, and then this is going to be, right, the cosine, this is going to be the cosine of 60 degrees, right? Okay. So force of gravity, yeah, 10 times 9.8. So that looks like 10.9.8, right? Yeah, okay. Cosine of 60 ends up being also 1/2. Cosine of 60 and sine of 30 are the same thing. You can kind of see because cosine, right, is adjacent over hypotenuse. Sine is opposite over hypotenuse. Sorry, adjacent over hypotenuse, yeah. So they both refer to the same side of a triangle, which is 1/2. So this ends up being, right, 10 times 9.8 times 40 times 1/2, which is going to be, what is that, 20, 200, was it 960? I think is what that is. I think that's right, 1960. There we go. Okay. That would be the amount of joules that gravity does in terms of work to push this thing down the incline. Now, that was a lot of work, you know, no pun intended. That was a lot of work to do all that trig and whatnot. There's actually a much simpler way to do this question, which I'm going to show you, and it helps you out to know the smart ways to do things. I say in physics, like it's kind of like there's 2 ways to skin a cat, which is kind of a weird pun anyways, but there are a lot of different ways to solve. Yes, good. Exactly. Yes, perfect. Yeah, that's what I'm going to go right into, Sandeep, for those that don't know. Okay. So let's remember, again, that work is equal to the force times the distance. And what you're doing, in this case, we figured out the amount of force that was going in the direction of the distance is what we were doing. You can also figure out the amount of distance which is going in the direction of the force. So when we did this, this FG cosine theta, right? That tells me how much of this force is going in the direction of the distance. Because and this is actually cool. This is why like components work the way they do, is that this FG has 2 components to it, right? This FG has what we would call like an FG perpendicular to the distance, and it also has an FG parallel. So this part of FG points in the same direction as the distance, and that if this is 60 degrees, right, that's FG cosine of 60, right? Because in that case, cosine of 60 degrees is equal to cosine is equal to the adjacent, right, which is FG parallel over the hypotenuse, which in this case is just FG. And so that's why FG parallel, let me move it over here, is FG cosine 60, right? And that's one way to do it. An easier way to do this is to figure out the amount of distance that's in the direction of the force, okay? And what we can do for that is that we see that the force points straight down, okay? So I'm just going to write that as just, okay, cool. And how much does that force point straight down? Just m times g. So that's just 10 times 9.8, okay? Now, looking at the distance, right? This block technically travels in this direction, but what I want to know is how much of that distance is in the same direction of the force. And that's just going to be the amount of height that it drops, okay? Which is just equal to 20. So now you can solve this right here and just be like, oh, cool. Well, the force points straight down. And I know that since the amount that the block travels in the down direction is 20, I can just write it like this. And this is also going to be equal to 1960. So, you know, this takes like a lot of time to do all this. It's cool. You should know how this works. But like, if you're smart, you know, you can just be like, aha, I already know how to do this. It's a lot easier for me to figure out the distance in the direction of the force than to figure out the amount of force in the direction of the distance. That's how that works. Love the sound effects. Yeah, cool.
Nice.
Thank you. Does that make sense? Does that make sense, guys? That's a trick you guys should know. That's a really fast trick that that'll help you out a lot. Okay, awesome. Right, and then what's it? Since there's no friction here, right? There's technically no loss in mechanical energy, and you know this by conservation of energy, right? The potential energy plus the kinetic energy here will equal the potential energy plus the kinetic energy here. So yes, cool. How much is work? So that's how that works. With someone who asked about work, Shreya, did that answer your question about work? Awesome, great, good. Cool. All right. Yeah, if you guys ever see a topic, you're like, I need a quick little like thing about that, I can do it. And honestly, it'll help everyone else out, even if they've already seen it, because I know all the tricks that you have to know for some of these things to just. There's always the graders are lazy, honestly, in this exam. You know, don't shoot me, College Board. But so when they write questions, they write them so that if you know the clever way, you can get the right answer very easily. They don't want to go through, you know, all this to figure out the answer. They want to just write down this and be like, cool. Did the student get the right answer? Yes. Cool. Move on. Okay. Let me see. These are the questions. Right. So that's work. Network is always equal to change in kinetic energy. That's always true. You could have seen that right here, right? So network is the amount of work. Do you think a 3 is good on a physics exam? Yeah, no, a 3 is great. Actually, they had a 1 sec. Let me show that for you guys. AP Physics, AP Physics 1. They had a statistics here. If you guys want to see some statistics, scoring distribution. Right, this was from last year. Okay, so these were the exam scores from last year. You can see that only the top 6.9% ended up getting a 5. Can we look to find the coefficient of friction or the force of friction given distance? Yes, we can, Salisha. That's totally cool. We can do that. So anyways, here. So I think College Board in general will consider a 3 or higher to be passing, okay? And that happened for about 42% of students, okay? So, you know, that's some pretty good odds. 42% is not bad, you know. It's not the best. It's definitely a hard exam. But you know, having a 3 is definitely doing pretty well. You need to, you know, you'd be in the top was it 58% of students if you did that. You're in the top 6.9% if you get a 5. 5s are pretty difficult. But you can see that the majority of, you know, there's a lot of bulk scores here around the 3s and the 4. Of course, a lot of people don't do so well, but I think a lot of people get forced into this exam, and because their teachers, like, I don't know, for whatever reason, get bonuses for having kids take the AP test, and then they don't actually even teach them for this. I have so many students that have come to me this week that are like asking some questions that like their teacher just hasn't even gone over it. I'm like, wait, you have the AP exam this week. How are you going to do this if you've never been taught it? But anyways, so yeah, get a 3. 3s are great. Yeah, AP language. Yeah, seriously. And actually, the reason why you guys want to be taking these AP classes is that the college credit is really, really useful because it gets you out of courses when you go to college, so that you're not having to take these basic courses again in college with 300 people in an auditorium. And you just get credit for it, and you can jump right into the harder stuff, or actually the more interesting stuff, honestly. And, you know, I'll speak from experience is that like, studying and doing well in the AP exam is a lot easier than spending 4 or 5 months in college taking the course at college, because you have a lot more exams, a lot more work, and a lot more. Yeah, you said I probably forgot it. Yeah, and it's a lot more effort. So you really want to do well in the AP exams. I took something like 20 or 30 of them. I forget how many I took, but I came into college with like 60 or 70 college credits just because I took every AP exam I could. And it really got me out of a lot of basic classes I didn't have to take in college. And, you know, it leaves more fun. It leaves more time to take, you know, fun classes. You don't have to take these boring classes again. Okay, cool. Let's see. Shrey was asking about, Celestia was asking about the coefficient of friction. Yeah, that's a good question here. Here's a typical one they always ask. Let me see. Where is it? Okay. Let's take our same block here. Let's take our same block. Okay, but let's switch it up. And let's say, and the is sliding down at a constant velocity. What is the coefficient of friction in the block and the incline? Okay. This is a classic question they'll give you. They'll say like blocks on an incline, it's at a certain angle and it's sliding down, and they'll either tell you what the acceleration is, or let's say that there's no acceleration because it's going down at constant velocity, and they'll ask you about what the friction is. So the way to do that is here. Let's take our diagram again. Okay. Okay. So good thing to always do is to draw right force diagrams for stuff. So here, let me not red. Let me get I want my red. I want this. Good. Okay. So You draw a force diagram right on this block. We have the force of gravity, which is going to point to the right a little bit, right? This is going to be the force of gravity. What we're always doing here, guys, is we're just like rotating it. We're like turning our heads a little bit. You know, if I were to rotate this, and the reason why we do that is because I want to deal with the forces all in just really X and Y. Because for this block, you have the normal force, which points up. You're going to have part of gravity. We're going to call this like FGX that pulls the block down. You're going to have FGY that pulls the block into the incline. And then if something is sliding down this way, which way does friction point? Left or the right? Up the incline. Good. Yes. Okay. This is a key point here. So this is force of friction. Yeah, there's a key thing here, which is that friction always opposes. Friction always points in the direction that opposes where the thing wants to go or where it is going. Okay. This can sometimes get confusing if, for instance, this question comes up sometimes. Here, just a quick little side tangent. Let's say we have two blocks, okay? Here, let's say we have block 1 and block 2. Yeah, elliptical orbits, cool. Yeah, we can get to that. Okay. If I'm pulling on this with a force, let's say like a force pulling and whatnot, and someone asks you, and let's say that there's friction between the two blocks. What direction is the force of friction acting on block 2? It says both sides. Close. He says, "Oh, there isn't any." Okay, well, let's think about this. Okay, so and this is a very they love to throw this. This is always like a tricky question. It's actually to the left. The force of friction is to the left, and I'm going to show you why. Okay, so let's say this is the only thing. Let's say this is smooth. Okay. The ground here is smooth. Okay. So if and let's say there's friction between the two blocks, and let's say that the two blocks move together. That's the other thing they have to tell you. Okay. If we look at block 1 here, right, and you write, this is always what you have to do, right? Sum of the forces. So the sum of the forces for block 1, right, is just equal to negative FP, right? And that's equal to M1 times A1, right? This is always the key thing. Yes, yeah, the force of friction be the force keeping M2 on the lower box. Correct, exactly. And I'm going to go over that. So if you look at just block 1, ignore everything about block 2 and whatnot, you would see that, oh, okay, cool. This block here, right? The first block has only the force pulling it to the right, okay? Now, what else is happening, right, is because this is on the ground, right, this also has what we say like a normal force pointing up, right? So that would be sum of forces in the X direction. And so sum of forces in the Y direction would be the force of the normal of the first block pointing up. Okay. Now, additionally, right, this second block, right, is on top of it. So the first block is going to feel a force of gravity from the second block. So we would say that in terms of Fy, it has a normal force pointing up. It feels a force of gravity from the first block plus a force of gravity from the second block. So this is also going to be minus Fg1 minus Fg2, okay? Both sides would have friction on the top box. I'll explain to you what we mean by both sides, okay? Yeah. Because this goes into equal and opposite forces, okay? So, and I'll show you. There is something different to this. So let's say this is for block 1. Let's look at block 2, okay? Looking at block 2, right, and we look at the sum of the forces, right? What we know, right, is that block 2 is definitely accelerating to the left, right? It has an acceleration to the left, which means that the sum of the forces need to also push to the left in order for this block to stay stuck to block 1 and move. So that should give you a hint right away that there needs to be some force that pulls block 2 to the left. Here, let's do different color for block 2. Let's do purple. And what that force ends up being is the force of friction between the first block and the second block. And so let's explain how that works. So this is going to have a force of friction that keeps it accelerating with block one. Because if there was no friction, this is like, have you seen the classic, like where like the guy like pulls the rug out from the what is it, from the bottle or something? Have you guys seen that before? There's a famous guy that does it. He's like an Asian guy. He's always on TikTok. Yeah, it's the table clock under the vase. Yeah, what he's called Mr. Something or something. This guy's hilarious. Mr. Chu. Once I just want to show up because you guys are gonna think this is funny. Was it Mr. I think it's Chow pulling tablecloth. Yeah, it's yeah, this guy. Have you guys ever seen this guy? This guy's hilarious. What is his name? Mr. Yukaza. Yeah, one sec. He's always so funny. He does things where he pulls things out from, well, he has a bunch of videos, but I can't find what's appropriate. But yes, yeah, this is a great example. But okay, so yeah, if you just pull the tablecloth, right, and there's no friction between the object and the object that's being pulled, this object will just stay right there. Okay. In order for this thing to move with block one, it needs to stick to block one, right? And that sticking is provided by friction. And that friction is going to provide a force, which is going to move this thing to the left, okay? That's the force of friction that block two feels. Now, because of Newton's second law, right, which says that for every force, there's an equal and opposite force, right? If there's a force of friction pushing block two to the left, block one is also going to feel that force of friction in the opposite direction, okay? So this is the force of we say this is the force of friction between like 1 and 2. So when I wrote out my sum of the forces here for block 1, I need to also write that the force of friction is going to pull it here to the right, okay? This is plus F force of friction 1, 2. What if the boxes were at rest? If the boxes are at rest, well, then there's no friction, right? There's only friction if this thing is moving, right? Because what you need is you need some acceleration, right, for there to justify that there has to be a force. Because look, if we look at the forces on box X, right, box X only is going to have the negative force of friction. I say negative because it moves to the left of 1, 2, right? And that's going to equal the mass times the acceleration, mass of block 2 times the acceleration of block 2, which, since the acceleration of block 2 is equal to the acceleration of block 1 because they're moving the same, that means that this force of friction, right, is going to be non-zero, right? Because this is non-zero if the two blocks are moving. Yes, so this is the important thing. So I know it seems counterintuitive, right? Because you're like, wait, shouldn't friction be pointing the other way because this thing is moving that way? But they always love to trip you up with this. This block wants to stay still. Friction is what causes it to move in an opposite direction to where it wants to go, right? It wants to stay still. Friction is pulling it to the left. In the same case here, right? This block would love to just fall down. Friction keeps it up, pulls it up a little bit. So that's the tricky thing I want you guys to know about friction is friction always pulls in the opposite direction of where it wants to go. Okay. Does that make sense, everyone? Yes. Okay, cool. All right. Again, we can break up this force, right? This is going to be FGY. This is FGX. And if we remember, right, from the equations that you need to memorize, right, this one, you can do it geometrically as well, but it's just fast to know this, you know. It's just to be like, okay, cool. This is just equal to, so this is FG, which equals MG. This is going to be the normal force, right? And then this is going to equal the force of friction. I say FS for friction, okay? So I know this is equal to FG sine theta. I know this is equal to FG cosine theta, right? And now what you do is you just say sum of the forces in the y direction, sum of the forces in the x direction, okay? So in the y direction, which is referring to this, I need the block to not be like falling into the incline, and I need it not to be like bouncing off to space. Like that would be bad. So I need those sum of the forces to equal the mass times the acceleration in the y direction, which is 0. I don't need it I don't need it accelerating. Okay. In that case, right, you have, okay, cool. So that means Fn points up minus Fg cosine theta. All right. Look at the forces in the x direction. Okay. I notice I have the force of friction pulling it to the left, right, which was up the ramp. So I'm going to say negative Fs. And then I have the force of gravity pointing in the x direction, which is Fg sine theta, pointing to the right. Okay. And I need all the sum of the forces in the x direction to also equal 0, because we said that it is sliding down at a constant velocity. Constant velocity means that there's no acceleration, right? So if there's no acceleration, there's no net force on it. Okay, so this is also equal to 0. Okay. Now that you have this, right, we can start doing some math, right? So Fg, right, remember, is equal to mg. Do you guys remember what the force of friction is? What's the force of friction equal to? Mu times Fn. Yes, very good. Very good job. Yeah. So, and important, this is mu k Fn, okay? What we mean are this is the kinetic, this is kinetic friction, okay? Which is a coefficient that you use when the object is moving, okay? A lot of times what you'll need to do is you'll need to check, first off, if there's even enough force to overcome the static friction. That's another concept that you guys should know. You can ask me if you need help on that one as well. But yes, we know this object is moving, so I'm going to say this is mu k, okay? And so I notice I have minus mu k Fn plus mg sine theta, right? Needs to be equal to 0. And then I'd be like, okay, cool. Well, I have m, I have g. I'm trying to figure out mu k. I have theta. I don't know what Fn is. Okay. Could you review that? I could review that. Let me do that right after this. I'll do a quick friction. Will take like 2 seconds, and then I'll go up to the other stuff, the orbital stuff. So Fn, right? I don't know from here, but this is a common thing we do all the time in physics. I take what I know from the y direction, and I look. Sorry, I take what I'm missing in one direction. Here I'm missing this Fn from x, and I look over in the other component, the other direction, y, and I'm like, oh, cool, Fn's just right here. And what I see is that Fn is equal to Fg cosine theta, right? If I just rearrange this. So Fn is equal to mg cosine theta. And I can now plug that in to here. So now what I have is, let's change our colors here. I have minus mu k, and then this is over here. Here. Mg cosine theta, and then we have plus mg sine theta is equal to 0, right? Okay. And then you're going to see this is actually a pretty cool thing that happens. Okay. So I can move all this right to the right. So now I have that mu k cosine theta is equal to mg sine theta. Here. And now to solve for mu k, what we end up seeing right here is m cancels with m, g cancels with g. So you can see actually that you don't even care like how heavy the thing is in order to figure out what this angle is, or to find out what this coefficient is. But you just get that mu k is equal to sine of theta divided by the cosine of theta. Which, does anyone know what sine of theta over cosine theta is? Tangent. Tangent of 30 degrees. Yes, good. Okay, cool. So this is actually an important thing. If you guys just know, this is a good thing to know. This comes up all the time. Is that if you have an object, it's on a block, and you want to know what mu k is, right? In order for this thing to be going down at a constant speed, that's just equal to the tangent of the angle of the incline. Okay. Everybody brought mass to the party. Yeah, dude. Yeah, they're like, no, where's all the mass? Okay, yeah. Okay. Okay. Yeah. Quick thing on friction, because this always comes up. I've seen it before. Let's say a block weighs, I don't know, 10 kilogram and is on a surface that has a coefficient of static friction of 0.6 and kinetic friction of 0.3. Love to ask this. And they'll say something here. They'll say, like, part A. They'll say, if the block is pushed with a force of let's say 20 newtons, what is the acceleration of block? Yeah, exactly. Yeah, if you're given a simple situation, Salisha, yeah, you can just literally just use tangent of theta. You may want to show a little bit more work for the FRQ if they ask that. But if you see that on multiple choice, just go for it. You're just done. Okay, and then this is always the next thing they say. Let me move this. This needs to be a little bit smaller. Okay. Let's say the block is pushed with a force of 80 newtons. What is the acceleration of the block? Okay. Maybe what that's this. Okay. So always good to draw your diagrams, right? So we got senior block over here. Okay. Has a mass of 20 kilograms, right? So that means it's going to have a force of gravity, right? Which is equal to mg, which is 10, right? Times 9.8. And it's being pushed with a force. Let's call this like the force push. Oh, and this is also what they always ask. They say, what is force of friction? Yeah, they always want to say this. This is, yeah. Okay. Now, you say G equals 10 in the FRQ 9.8. Is that fine? I don't know that, actually. I would hope it is. I mean, it's close enough. Some teachers, yeah, use 10. I use 9.8 just to be safe. Why is FG going to the right? It doesn't matter. It's FG could be pointing to the right or it could be pointing to the left. It's just a convention. I'm having the force point to the right. The important thing is that the force of friction is pointing opposite, right, to the force that I'm pushing. Oh, sorry, this is FG. Oh, I'm so bad. You're so right there. I'm sorry. This is FP. Okay, sorry. FP, force pushing. Okay. And this is equal to 20 newtons. Okay, good. Yeah, 9.8. Go with 9.8 to be safe. Okay. All right. Okay. So what you guys know, right, for the force of friction is that's equal to either mu s times Fn or mu k Fn. Okay. And that depends on whether the object is moving. That would be kinetic. You use the kinetic coefficient, or the moving, or object is stationary, and then that's when you're gonna use the static coefficient. So here we have coefficient of static, right? Mu s is equal to 0.6. Why is my font so big? 1 second. Mu s is equal to 0.6, and mu k is equal to 0.3. Okay. So the first thing you always do, if you want to figure out whether this thing is moving or not, and the way to do that is to check if the force that you're pushing on exceeds what the maximum force of friction could provide to fight it. Okay. So what I like to write is I like to say like Fs max. Okay. That's the maximum force of friction that can be provided to keep this thing still. Okay. And that's always equal to mu s Fn. Now, if force of gravity, right, is pulling down with 98 newtons, you guys know that the normal force, right, is going to pull up with 98 newtons because this object is not bouncing up and down. So this is going to end up equaling 0.6 times 98, which I have a calculator here somewhere. Where are you? There you are. What is this? 0.6 times 9.8. And that's times 98. My bad. 0.6 times 98. So that's equal to 58.8. Okay. So that's equal to 58.8 newtons. Okay. So is this object going to be moving? Yes or no? No, right? Good. This object does not move, right? Because the force that is pushing on it, 20 newtons, is not enough to fight the force of friction, which is up to 60 newtons that could fight it going back, okay? So yeah, so when they ask for the acceleration of the block, you're going to say A is equal to 0. Okay, here's the next question. What is the force of friction on this block? Good, Michael. 20 newtons. Yeah. Good. 20. A lot of students will start saying it's this number. They'll start saying it's 58.8, and that's not correct. The reason being, friction is what we call a smart force, which means it only applies the amount that it needs to be. It is negative. Good. It is negative. The negative is not. Yes, negative is correct because it's pointing to the left. I totally agree with that. But usually, if I wrote the question better, I would have said the magnitude. Because if, for instance, I had my pushing force going this way as being negative, then this would be positive. But yes, technically it's negative. Yeah. But yeah, the important thing is that, yeah, it's equal to 20 newtons is the force of friction. Okay. Because the friction only applies the amount of force it needs to keep this thing still. If you had said it's 60 newtons because you calculated the maximum amount of friction that it could provide, then what would happen is this object would just start going really quickly to the left, right? You would be like pulling on it and it'd be going like whoop the other direction, which is like no. So just a thing to watch out for. Okay. So good. That's the force of friction equal to 20 newtons, right? Okay. And then, so that's what you always want to check. You want to check, first off, see what your maximum frictional force is, see if it's greater than it. It's not, it stays still. Similarly, so here now we bump the force up to 80 newtons, okay? So if the pushing force is now 80 newtons, right? I see that this is much greater, right, than the maximum amount of friction that's maximum amount of force that static friction can provide. So this thing is going to break. It's going to start moving, okay? Now, what happens is now that it's moving, okay, now that this object is moving along its way, right, with the 80 newtons, right, we're going to use a different coefficient to calculate the friction, and that's going to be Fs is equal to mu k Fn. And so usually what happens is, like, for almost all substances, is that mu k is always going to be less than Fn, right? So now this is going to end up being 0.3 times 98 is going to equal the force of friction, okay? Which is 0.3. That's going to be 29.4 newtons, okay? And so now when you're calculating the acceleration of the block, right? Again, sum of the forces in the x direction, which is the 80 to the right minus the 29 to the 0.4 to the left, has to equal the mass of the block, right? Which is 10 times the acceleration. So you just do 80 minus 29.4 all over 10. And let's see if I can do that in my head. That's 50.6. So 5.06, right? A is equal to 5.06. Is that right? Yeah, 5.06 meters per second squared. Cool. Does that make sense? That's a pretty good quick review of like what you need to know between static friction and what is it? Static and kinetic friction. Yeah. Okay, cool. Let's see. What was the first one? Okay, so we did force. Good. We did that. Okay, so Anaya said, can you review vertical circular motion like when a ball in elliptical orbits? Okay, that's a good one. So let me think. Do you guys probably have the classic Here it is. A roller coaster starts at a height of, I don't know, let's say 100 meters. And goes down to a loop-de-loop with a radius of, let's see, radius of 20 meters. Okay. If a person on the roller coaster weighs 100 kilograms, how much will, how heavy will they feel? This is always the question they ask. How heavy will they feel at the top and the bottom of the roller coaster? You guys have seen this one before, right? Yes, for part A or B. FP was 80 given in part P. So no. So this was the difference. In part A, I said that we just pushed it with 20 newtons, and in part B, I said we pushed it with 80. So the first one, we didn't have enough force to break it, so it stayed stuck. And then in this one, I definitely had enough force to break it. 80 newtons was a lot, and that's why it started moving. Okay, cool, awesome. All right, so this is a very, very common question, and this is kind of a cool. How many of you guys have been on a roller coaster? Like I used to like. The first time I was on a roller coaster was like 2 years ago, and I'm like 31. So like, it's you've been on a roller coaster, yeah. I'm like super scared of heights, which is always funny because I'm not scared of many other things. You have a Six Flags trip. Wow, that's super cool. Yeah. Yeah, I think ours was at a Six Flags as well. We did what's called Colossus. Okay, cool. All right, so here's what happens. We got roller coaster people located, what's 100 meters up, and then they're gonna go down, and then we have a loop-de-loop. This. That has a radius of what is this? This is a radius of 20 meters. Okay, cool. All right, how heavy the feel at the top and the bottom? Okay, so all right, the important concepts to know here, right, is that for anything moving around in a circle, what is the acceleration for something that's moving in a circle? You guys know that? V squared over r. Yeah, good. So the acceleration, we call it centripetal acceleration, is equal to v squared over r. Okay, that's always what you need to know. Sometimes people will say oh, centripetal force is equal to mv squared over r. I mean, technically yes, but centripetal force is not a force. So don't do that. So the best way to do this to not ever get caught up on things is just use this, and I'll show you how. Okay, just always remember that the centripetal acceleration is v squared of r, and then we'll figure out everything else. All right. Okay. So what I want to know is to see how heavy someone feels here at the bottom and how heavy someone feels here at the top. Okay. Centripetal force is a net force. Yeah, it's good. It's not an actual force. Yeah. Right. Yeah. So what was I thinking here? Okay. Yeah. Okay. There are going to be two different force diagrams we're going to draw here for when they're at the bottom and when they're at the top. All right. Maybe it's also a good thing to go over. Do you guys remember what force corresponds to how heavy you feel? Not FG, close. FN. Good. Yes. This is the classic elevator question, right? If you're standing on a scale and you're in an elevator, right? There's always FG pulling you down, but FN is going to vary, right? whether you're accelerating up, accelerating down, or whether acceleration is equal to 0, okay? When acceleration is equal to 0, this means that Fn is equal to Fg, right? Because your normal force has to be equal. Good. It pushes up on you, right? You feel heavy because you feel the ground pushing up on you. And it's kind of weird. If acceleration is positive, that means that Fg is greater than Fn, right? And if acceleration is negative, that means that Fn is or Fg. Wait, acceleration is up. No, my bad. This is Fn is greater than Fg. This is Fg is greater than Fn. Or who will say is Fn is less than Fg. Okay. So if something's accelerating upwards, you feel heavier because the normal force is greater than the force of gravity. Reason for that, right, is if you're accelerating upwards, since the sum of the forces is equal to Fn minus Fg, which is equal to ma. If A here is positive, if A is going up, that means this difference needs to be positive, which means that this must be bigger than this. And if Fn is bigger than Fg, then you feel heavier because your normal force is bigger than what it is when Fn is equal to Fg. Do not put Fc in a free body diagram. It's what's Fc? Yes. Yeah. Good. Okay, cool. All right. So that's an important thing to know. Okay. So let's look at what's happening here down at the bottom. Okay. So let's zoom in. Okay. So when we're looking at the bottom of the roller coaster, all right, we have a couple forces, right? I have the force of gravity, which is pulling down, right? And then I also have the normal force, right, which must be pushing up. Those are the only two forces that act on you when you're in the roller coaster, okay? I know this force of gravity, right, is going to be equal to my mass times 9.8. So that's going to be 100, right, times 9.8, okay? And then the question here is, like, what is my normal force, okay? Well, what I know for at the bottom, right, is that the sum of the forces in the y direction, which is going to be Fn minus Fg, that has to equal my mass times my acceleration. Okay. Now, you might be saying at the bottom, you're like, oh, your acceleration is 0 because you're just chilling there, right? You know, there's no acceleration. But what's happening is you are technically moving in a circle. If you're moving in a circle, there is always a centripetal acceleration that pulls you towards the center. This is called AC. And that acceleration is equal to v squared over r, where v refers to the tangent velocity. I think they call this sometimes like v perp. So, you know, that's what this is. This is like v perp. Okay. So acceleration here is now going to become v squared over r. All right. So now when I start putting in my numbers, I'm going to have, okay, cool. So the normal force, how heavy I feel, is equal to the force of gravity, which is this is how heavy I normally feel, like just on the earth, right? If you're just chilling on the earth right here, Fn is equal to Fg, right? That's how heavy you feel. So that's just equal to Fg, which is 100 times 9.8 minus plus m, right, which is 100 times v squared over r. R is the radius of our circular motion, which in this case is 20 meters, because that's what we said the radius of the roller coaster was. Okay. Here's a good question, though. Okay, so in order to get this, right, to get this answer, I need to know what v squared is, where v is my velocity right here. Does anyone know how I'd figure out what the velocity of myself is right here? Conservation of mechanical energy. Yes, very good. So what I know is that, very good, Michael, the potential energy plus the kinetic energy here has to equal the same potential energy plus kinetic energy that is here, okay? And actually just for any point in time, you need this to be constant, okay? So what we can always do is use one point in time where we can figure out the total energy, and that's the time here. where mu is equal to mgh, right? So this is going to be 100 times 9.8 times 100, okay? The kinetic energy, if this, we're going to assume this starts at rest and this is 0, okay? So this is always going to be this is going to be our total mechanical energy, okay? Which, what is that? That's 2 zeros, so that's 1, 2, 3, 4. Okay. 10 to the 4. Yeah, that's 98,000, which is equal to 9.8 times 10 to the 4 joules. Okay. Now, when we get to the bottom here, right, all of my potential energy has now gone to 0 because now we've dropped the full the 100 meters. The height here is equal to 0. So that means that I need to have all of my energy now going into kinetic energy. So I have 1/2 mv squared is equal to 9.8 times 10 to the 4th, right? This is equal to 100. So this becomes 19.6 times 10 to the 4th. Divided by 100 is 19.6 times 10 to the 2nd. And then you got to square root that. So we're going to get a velocity. Let's get a velocity for that real quick. So v is equal to square root of, and actually, ooh, this is actually kind of cool. No, we can actually leave this. I'm going to leave this as v squared. I'll show you why I'm going to leave it as v squared. So v squared is equal to 19.6 times 10 to the 2nd. The reason why I'm going to leave it as v squared is because I just need to put v squared in back for that anyways. So it doesn't make sense to square root it and then just square it again. All right. But yes, so this is going to be 98 plus 5 times 19.6 times 10 to the 2nd newtons. Okay. So there we go. That's the first answer. This is how heavy you feel. So you feel your regular weight plus like a lot more weight. This is a lot. Like what is this? Like 5 times 19.6 e to the 2nd. That's 9,800, right? And then divide that by your mass, which was or divide that by divide that by 100. Oh, so that's 98 G's. Wow. Yeah, that would be that would kill you. Have you guys ever seen this? What is it called? It's called like the suicide roller coaster. Someone did this. Yeah, the euthanasia coaster. Someone in physics designed a roller coaster where like this would be the last ride of your life, but because they can also be unreasonable. Yeah, this would kill you a lot. Yeah. So someone did this actually. They designed a roller coaster where like this would like get to smaller and smaller and smaller radii, and you drop from such a big height that eventually your body would just like be like, nope, I'm done, because like this is way too many G forces. It's kind of surreal, but yeah. So yeah, and the reason why honestly this roller coaster would kill you is that like this is a very small radius, 20 meters. I shouldn't have made it this small, honestly. Okay. All right. So never mind dying at the bottom. Okay, let's look at the top real quick. So at the top, you have the force of gravity, which is going to be the same 98 newtons pulling down. But now the interesting thing is that force of gravity and the force of the normal both point in the same direction as the centripetal acceleration. So here, actually, sorry, so this is also AC, and now they both point in the same direction as AC. So what changes in your equation at the top is now you have some of the forces in the y direction, right? Is negative Fn minus Fg is equal to negative mv squared over r, which all these negatives I could just get rid of and just say, okay, cool. Fn plus Fg is equal to mv squared over r. Good. It is kinetic and potential. We'll show you why. Okay. So again, you can figure out the normal force, right? So normal force is now going to equal to mv squared over r minus Fg. Okay. And same thing. This is 98. This is 20. This is 100. Figuring out V is going to be different here, okay? Because now we're at an in-between step where like we are going to have potential energy because we're still kind of high up, and we're also going to have kinetic energy because we're still moving. Okay, so in this case, you're going to have mgh plus 1/2 mv squared has to equal the total energy, right? 9.8 times 10 to the fourth. And for mgh, what's the height of the object when they're at the top of the loopy loop? 40. Good. Yes. Radius here is 20, guys. So it's 20 plus 20. So this is 40, right? So you're going to have 100, 100 times 9.8 times 40 plus 1/2 times 100 equals 9.8 times 10 to the 4. Cool math tricks. Cut the hundreds out. Make this a 2. 1/2 m. Sorry, there's a v squared here. Okay, but then I can't. Yeah, there's no more math. There's no more nice math I can do. So 980 minus 9.8 times 40 equals that times 2. So I'm going to get that v squared is 1176. Where is it? So I get v squared equals 1176. Okay, so now when I plug that one into here, right, this is going to be 1176 for v. Okay, and so now you have 100 times 1176 divided by 20 minus 9.8. You get 5870 newtons. Cool. Which is, not that many. Like 5,000 newtons, what's that? Divided by, let's see what that is. Divided by your weight. Fn. Yeah, divided by your weight. We forgot the acceleration. Or I can hear it. Let's divide it by g to figure out what that mass is. So, no, that's still a lot. What is it? V squared. 100 times. Oh, actually, no. I can just divide this by 100. I'm dumb. Sorry. Oh, that's still a lot, though. Yeah, 58 F equals. Yeah, that's still a lot. That's a lot of G's. So, yeah, it's still also not good. you would also, 5,000 newtons is not a good amount of force to be applied to you. Yeah, that's 58 meters per second squared, right? Wow. Oh, yeah, that would hurt. Okay, never mind. Yeah, don't get hit with don't ride this roller coaster. It's a very bad idea. You'll die at either the bottom or the top. But anyways, that's how that would work. And what you see is that the amount of you feel less light. Sorry, you feel lighter at the top than you do at the bottom because the normal force is less. Albeit you're not going to feel anything because you're going to die because this is way too many newtons. But that's what happens when I design a question on the fly. Okay, cool. Let's see. I probably got time for like one more. Who has something else here? Vertical circular motion. Elastic collisions, energy, and a spring between two boxes. Okay. Let me think if I can do all three of these things in one. Yeah, I want to see if I could do this. Yeah, one sec. Energy, spring. This was kind of energy, Eddie, to be honest. This was a lot of energy. This was, potential kinetic, and then this is potential kinetic. Spring between two boxes and a collision. Okay. Yes, I think we can do this. Okay, here. All right. Yeah. Okay. Two blocks of mass. 100 kilograms are going. Oh, actually, let's make them. Yeah, here. Let's make them different. Let's make them different. 2 blocks of mass. Let's say 50 kilograms and 100 kilograms. Right? I want to make them smaller. Let's make them smaller. 5 kilograms and 10 kilograms are going towards each other with a velocity of 8 meters per second each. So one's going 8 meters per second this way, one's going 8 meters per second this way. Okay. If one of the blocks has a spring on it, and when the 2 blocks collide, the spring only yeah, and this will have Eddie, this will have energy in it too. Yeah, this is something where like this is gonna have all 3 of you guys said things. This is gonna have all 3 things in it. The spring only compresses by let's say 10 centimeters. What is the spring constant of the spring? The blocks stick after colliding. What is the velocity of the blocks after the spring has reached equilibrium? Okay, cool. All right. This will be the last one, last question, because this is a monster of a question, but I'm putting a lot of concepts into it. Okay. So stick around. You're going to learn a lot of different things from this one. Okay. So let's say we have, I'm going to say this is block A. So I'm going to say mass A. And then we're going to have another block, which is mass B. Okay. One of the blocks is going to have a spring on it. Okay. And they're both careening towards each other at a velocity, which I'm just going to call V, which is 8 meters per second in this direction. And this one is also going at V is equal to 8 meters per second. Okay. The first thing I'm asking is they're going to hit each other. Okay. And I want to know how far that spring collapses. I want to know that if the spring only collapses 10 centimeters, what is the spring constant of that spring? Okay. So this is going to be the before. And then here, let's draw the after. So then this is after. Here, let's erase a little bit of this. Okay, and this is actually cool. We could actually figure out what the velocity is. Okay. And then the 2 of them are gonna stretch out again. You get how like they're gonna hit each other, they're gonna like compress a little bit, and then they're both gonna like move together. And we're gonna get to here, which is like the third situation. Okay. First thing we gotta do. All right, we got the blocks moving towards each other, right? And we want to figure out when they collide, right? How much, what does the spring constant need in order for this thing to only collapse by, what is it? I said 10 centimeters. So yeah, by 0.1 of a meter, making sure that everything's always in meters. Okay. The way to do this is via conservation of energy. Okay. So what we're going to have here is we're going to have conservation of energy, but we now have 3 things. Okay. We'll actually only have 2 because we don't have any gravitational potential energy because these things aren't moving up or down. But they're moving left to right. So the 2 energies we're going to have are going to be kinetic energy and spring potential energy. Okay. So I'm going to say we're going to have kinetic energy and spring potential energy. Okay. So at the beginning, All right. And also, we should also look at what like the momentum is. Momentum is also very important here. Okay. So in the beginning, let's look at what my total energy. So energy total, right, would be equal to 1/2 ma v squared plus 1/2 mb v squared. I'm just going to use v because they're the same velocities, right? Okay. And that's going to be constant throughout the system. There's 0 spring energy, right? Because this spring is not hitting anything yet. It hasn't been compressed. But if I look at the momentum, right? So let's look at P tote. And this is always, you always got to like figure out whether like energy, potential energies conserved, kinetic or kinetic energies conserved and whatnot. This P tote is going to be equal to ma times v minus mb times v. Okay, right? Because I have this thing moving to the right, momentum is going to be to the right, positive, and this thing is moving to the left, momentum is negative. Okay, that's those two things are constant. Okay. Now let's move this. Okay. What's going to happen, right, is that these two objects are going to hit each other and the spring is going to collapse a little bit. Okay. So now what I'm going to have is an energy total, right? Where when these two things have collapsed to their max, right? What are the velocities of these blocks going to be once they hit each other and the spring collapses the maximum amount that it's going to collapse? Zero. Good. Yes. Yes. Okay. This is going to be 0. This is going to be 0, right? Okay. But we're going to have, right, some we're going to have some spring energy still happening here, right? Okay. So oh, actually this is interesting. Ooh, they can't be 0. They can't be 0 actually. No, I take that back. They can't be 0. Because this is I may have made something more complicated than I needed to it. The problem is that like momentum always has to be conserved. I think in this case, right? Yeah. Or is friction is let me think. The spring hits something. Oh, but this is a non-conservative force is what this is. Okay. Okay. Actually, yes. Let's keep it as this is 0. Okay. These two are 0. Okay. And then this has to be 1/2 k times x squared. Okay. So, what I know, right, is that I know what x is. X is the maximum amount that this thing compresses, which is 0.1, right? And I know what the energy total is from before. That was here. So this was equal to let's get a number for this. This is 1/2 times, what did I make them? I made them 5 and 10. Oh, geo, come on. So 5/2 times 64 plus 5 times 64. What is that? That's 7.5 times 64. Let's see. Okay, so that's 480. Okay. So I know that 1/2 times my k, which I'm going to figure out, times 0.1 squared has to be equal to 480. Okay. So now what you can do is you can solve for k here, right? Multiply by 2. Divide by 0.1 squared. Okay. So 960 divided by 0.1 squared. Okay. And that ends up equaling, yes, 96,000 newtons. I think, wait, are they Newton meters? I think that's a k times x. No, it's newtons over meters. Yes, there you go. Cool. Where did the 480 come from? Okay, sorry. Yeah, let me show that. Okay, so when at the beginning here, Cheyenne, I figured out what the total energy of the system would be, right? Which is the kinetic energy of the block A plus the kinetic energy of block B, because there's no other energies, right? This, right, was 1/2 times the mass. This was equal to 5. This was equal to 10. So 10 over 2, or sorry, so 5 over 2, right? That's the 5/2. Velocity is 8, and 8 squared is 64. And then here we had 1/2 times 10, which is 5, times the velocity, which is 8 squared, 64. And then I added these up. So 5/2 plus 5 is 7.5 times 64, and this is equal to 480. Sorry, I should have written that. It's the total energy is what it is showing. And because what I know is once these two things have collided and the spring is like being compressed, that means that the total energy also has to be equal to 480. And so what I said here is that when this thing is at its maximum compression, that means that the velocities of the two blocks must be 0. Difference between non-conservative and conservative forces. Good. Non-conservative forces are forces that are lost due to like forces that basically lose energy, like due to heat. An example of that would be friction. Friction is a non-conservative force. I believe spring energy is a. Let me see. Spring force is conservative. Let me see. If the potential energy of any force is 0, then it must be non-conservative. It says spring force is conservative. Yeah, ideal spring is conservative. Okay. Oh, yeah. Did my audio stop working? Can you guys hear? Yes, you can hear. Okay, good. All right. Okay, cool. Yes, so now we got down to this situation, right, where we said the velocities of the two blocks must be 0 if they've compressed the most, and I wanted to only compress by 0.1. Yes, right, otherwise heat is generated, yeah. So that's where I get the 1/2 kx squared has to also equal the total energy that we were at, right, which was the 480 joules, okay? So I solved for this. 1/2 kx squared is equal to 480. Move some stuff over, divide, and then you get what k would be, which here is 96,000. Gravity is conservative too. Yes. I think what it means by conservative force is that that if you apply the force in one direction and then you apply it in the opposite direction, that no potential energy can be lost. Okay. The example for this is gravity, right? If gravity is a force pushes something down and then you pull it back up, conservation, the potential energy stays the same, right? Because none of that energy was lost into anything such as heat or whatnot. I think with a spring too, and yeah, I saw that. Yeah, if you compress a spring and then decompress a spring, the energy should return in the full amount that was taken away or given. Okay, cool. All right, so now we got that, the 96,000. Okay. So the next question, right, is that, okay, once they've now stuck together, what is the velocity of the two blocks together? And now this comes back to conservation of momentum. Okay. So let's remember that the total momentum before, right? So so let's get a number for that. So the total momentum before, right, was equal to 5 times 8 minus 10 times 8, right? Because this had 8 pointing to the left, and this had 8 pointing to the right. This is 8 pointing to the left. So you end up getting a total momentum of 5 times 8. So that's equal to 40. Yes. Okay. Yeah. 40. What is that? Meters per second. Kilograms meter per second. It's a weird unit. So now in this situation, these two blocks are stuck, right? So when I figure out the momentum here, okay, this is also need to be equaling to 40, but that's going to be MA plus MB, right, times the velocity of them together, okay, which in this case is going to be the 5 plus 15 times the velocity. Okay, and sorry, this was negative. Sorry. See how this was 5 times 8 minus 10 times 8? That's negative 40. Sorry, I screwed that up. This is supposed to be negative 40. Okay, so I get negative 40 is equal to 5 plus 15 times V. So negative 40 is equal to 20 times V, or V is equal to minus 2 meters per second. So these two blocks move to the left. Where? Okay, good. You're right. There's no 15. Thank you for checking me on that. Oh yeah. This is also why I say it's too funny. I have some students that like if they have a test, like, and this is why this is our last question, we're done. They'll ask for me to teach them or something, and they'll be like, I want to book 3 hours with you. And I'm like, you're gonna be done by hour 1, maybe hour 1.5. Like there's only so much learning you can do in like one like sitting down time period, which I start feeling really bad for some of these community college students because their summer classes are like 4 hours long per day. And like you cannot learn something in 4 hours. Max, maybe 2 hours, maybe. Like after an hour, hour and a half, your brain starts being like, I don't want to do this anymore. Like this is a lot of stuff. So as you'll see, even I'll start making mistakes here because after enough time, I'm just like, no. Okay, so this is not -2. Thank you for pointing that out. No, that's good. You guys are staying on top of it. What is this? See, even my brain can't do 40 divided by 15. I think it's 2.6. Yes. Okay, good. negative 2.667 meters per second. Yes. Okay. Awesome. Cool. Okay, cool. Was that helpful for you guys? I really like that. I like when you guys say like topics and then like I can go through and create problems. Yes, very good. Awesome. Yeah. It's I've taught physics for so many years, like probably 14 years at this point. I've seen every exam that gets asked. I've seen all the questions and whatnot. I know what they're gonna throw at you. So yes. Good luck everyone on the test. I hope you guys do amazing. You're all gonna get 4s and 5s. Maybe you guys will get some 3s, but like you guys are rock stars. Like the fact that you even showed up to this, you're very welcome. Will this recording be in the section? Yes, it will. Give it a little bit of time. It needs to render. I think Source says it takes a couple hours for them to render it. And we went for a good amount of time today, so that might take a little bit longer. But yeah, may the odds ever be in your favor. Yeah. Okay, awesome. Good luck, everyone. I might do more classes in the future. So if you liked this whole Lighthall thing and whatnot, stick around, look around. There are people always like throwing courses up. I may do some stuff over the summer. I might do like some intro calc courses or whatnot. I teach everything. Again, join the Discord if you want to get more help with stuff. If that's the link to that, and then here's the link to the Twitch. Where I tutor for free, an hour every day, Monday through Thursday. You can ask me whatever. So if you need help with your science classes, biology classes, chemistry classes, come on by. I'll help you out, and you guys will do great and everything. Cool. Okay, good, awesome. Love you guys. Best of luck with everything. I'll see you guys around. Peace.